we touched upon a very important topic called as flip-flop. What is the difference between the latch and the flip-flop is? Latches are instantaneous and they are edge triggered, they are level triggered combinations of gates. Whereas flip-flop, they are not spontaneous, but they are controlled by the edge triggered clock. Flip-flop has got a better control when compared to the latches. Okay. So we studied about the triggering thing, and then we just created some block diagram for flip-flops. How do you identify a flip-flop and a latch? You will have a clock in case of a flip-flop, whereas in case of latches, you will not have. You can have a positive edge triggered flip-flop or a negative edge triggered flip-flop. And how do you identify that? Is you will identify that with the bubble that you have across your clock. If you have a clock bubble in your clock, then they are called as negative edge triggered flip-flop. We saw an SR flip-flop. The most important thing of an SR flip-flop is its input when you are having S and R equal to 1. Okay, this is an invalid input. Our every attempt must be such that these invalid inputs must be eradicated. Okay, so as design engineers, we must always think about how to avoid these inputs. Now, for that, what we did, we created a characteristic table. Now, characteristic table will not give you any detail. I mean, it will give you just an overall picture of how your SR flip-flop works in terms of your present input. So if your output is a next state, your next state will be represented in terms of present states. So we created a characteristic equation, and to create a characteristic equation, your characteristic table is not sufficient. We have to create a state table now. So your state table, what is the difference between a characteristic and a state table is, your state table will have your present state as also one of the input in case of the truth table, state table, right? So here your present state is also one of the input. Based on that, you create the present state, the next state output. So you create a complete K-map, and then we get the characteristic equation. So then so this is how we implement an SR flip-flop. This is a clocked SR flip-flop. And then from clocked SR flip-flop, you can also implement the D flip-flop. I mean, what is the difference? I mean, you short this S and R, but you invert this R, right? So like this. This is what is your D flip-flop is. Now we have to create a characteristic table for a D flip-flop. Please always remember your characteristic table. In your characteristic table, your next state output will be in terms of your present state input, which means that your Q of t plus 1 will be in terms of Q of t. But whereas in this case of a D flip-flop, your next state is independent of your present state. So we created a state table here, and then from the state table, we created the Boolean expression, and you will see in the Boolean expression again that your next state is not dependent on your present state Q of t. So till this we saw in the last class. So 6 minutes of a nice introduction. Now let us move on to JK flip-flop. What is this J and K flip-flop? Obviously, I started off explaining you about the disadvantage of a SR flip-flop, right? In SR flip-flop, we must avoid this input, right? So in this input, how do we avoid this input in case of a JK flip-flop? So which means that A JK flip-flop is a refinement of an SR flip-flop where we remove this indeterminate state of an SR flip-flop. What is the indeterminate state? When S and R is equal to 1 and 1. Now, how do we do this? How do we remove this is, we are going to give a feedback mechanism. Feedback in the sense, you are having S and R inputs like this, right? So you take the output of a Q bar output is here. You take the output of a Q bar and feed it to S. And your Q output is here. You take the output of a Q output and feed it to R. So this is the logic. Okay. So as you see here, that Q and Q bar are fed back to the pulse steering NAND gates. Please remember that you are having a NAND gates here. Okay, so you are feeding your Q and Q bar back to this S and R flip-flop, and this becomes a JK flip-flop. Okay, let's see how it is going to work. Before that, some characteristics of JK flip-flop. So your inputs of a JK flip-flop will very much behave like an S and R, which means that S is for set and R is for reset or clear. So S is equivalent to J, which means when J is 1, we are setting the flip-flop, and when K is 1, we are clearing the flip-flop. Okay, so J and K, the equivalent values are S and R are the equivalent values. In JK flip-flop, you will not, the most important thing is you will not have any invalid state. We will see the operation now. Now, which means when J is high, obviously K will be low, right? They will be complement of each other. When J is high and K is low, you are setting the flip-flop, which means your Q is 1. When K is high, you are resetting the flip-flop, which means that your Q is 0. When Q is 1, what does it mean? Your Q bar will be 0 because they will be complement of each other. When Q is 0, your Q will be 1. They will be complement of each other, right? When both are low, they will follow the SR flip-flop only, right? There will be no change. Now comes the last case. When J and K both are high, which means equivalently S and R both are high, 1 and 1. In SR flip-flop, 1 minute. Yeah, sorry. So in J and K, your S and R are equal to 1. In J and K, what will happen is your inputs will toggle. What input will toggle? If I'll just let me not jump directly into the complete truth table. I'll just tell you what happens. When Q is 0 and J and K are 1, your present state will get toggled in your next state, which means 0 will become 1. Your 1 will become 0 when you have 1 and 1, right? So which means this is toggling, right? This is toggling. So this is what will happen, and this is how your circuit will look like. If you go deep into the circuit, you will not understand what happens to S bar, R bar. You will confuse. But however, I will explain how this works. Now, first look at the construction now. In addition to J and K, that is the clock and J input, your Q bar output is fed back to J input here, and your Q output is fed to the K input here. Okay, so and this creates your J and K equal to 1 at the toggling state. Now, what is the difference in the connection here? The difference in the connection here is now this S input here, it should be S input here will have J and Q bar dot, and your R input will be K and Q, right? R input will be K and Q, and S input will be J and Q bar. Now, maybe I'll explain. this particular part. If you look at S bar and R bar, definitely you are going to get yourself confused. But still, however, I will attempt to explain. Okay. Now, what will happen here? What will be this particular input here? This particular input, which is nothing but your S bar, will be equal to Q bar, am I right? Q bar and dot J, the whole bar, right? Because this is an AND gate. So this is equivalent to what? This is equivalent to Q plus J bar. This is equivalent to Q plus J bar, which means that your Q depends on obviously the values of Q and J bar, right? So that's why I said don't get deep into the internal circuitry of the SR flip-flop, because you are very much likely to get yourself confused. But however, we will explain this particular part of your circuit as we proceed in this particular section. So right now, I think you must be able to understand that your feedback here is from Q bar to J and Q to K, and this is going to alter your next state outputs. Now let's create a truth table. We will come back to that internal part later. Now, how does your JK flip-flops state table works? Please look at the terms I am using. I am not writing a characteristic table, I am writing a state table. So when your J and K are 0 and your present state is Q, right, there will be no change, right? Because J and K is equivalent to S and R, there will be no change, right? And when J and K are 0 here, and if your previous state is present state is 1, there will be no change. Here also it will be 1, no change. Now, when J is 0, it means K will be 1. We are resetting it. So Q is 0. Whatever may be your present state, we are not bothered. So here also, when this is 0 and 1, we are resetting it. We are not bothered what is here. Similarly, the case for setting. When J is 1 and K is 0, when J is 1 and K is 0, we are not bothered about what is your present state. All we need to look at is we are setting our flip-flop. Now comes the last case. When J is 1 and K is 1, if your present state is 0, the 0 will get toggled to 1. You are toggling your Q. Similarly, when J and K are 1 and your Q is 1 here, we are toggling to 0. Your Q value is getting toggled. Okay, so similarly, it is very much similar to your RS flip-flop, except that JK value is 1, 1. Now, what will be the characteristic equation for this? We have to just create the K-map for this. So when you create the K-map, right, so these are the values of 1 here. Right, so we are having 1, 1, 1, and 1. There should be 4 ones, am I right? Oh, there is some, yeah, there should be 4 ones. Yeah, that seems to be, let's see. Okay, I should erase this because okay, so 0 corresponds to 0, 0, 1, 1, and here it must be no change. It must be 1 here. Yes, it must be 1 here. Okay, so but still, now this is easy to do, right? So this combination and then this combination, but the Boolean characteristic equation will be the same. K bar Q plus J Q bar. So your characteristic equation in terms of next state is Q of t plus 1 is J Q of bar of t plus K bar Q of t. Okay, and now the characteristic table. This is a characteristic equation in terms of next state, present state in terms of next state in terms of present state. When it is 0, 0, there will be no change. So Q of t will be there. When it is 0 and 1, we are resetting it. 1 and 0, we are setting it. When it is 1 and 1, we are toggling it. And when your clock is 0, whatever may be the inputs, we are not bothered. Always your previous state remains as it is, right? So this is how your characteristic table for a JK flip-flop is. Now, there is one more flip-flop. What is that is, we are going to exploit this toggling function. So meaning that we are going to create a flip-flop called as a T flip-flop. What do you mean by a T flip-flop? T means toggling flip-flop, right? So we will use a JK flip-flop. Okay, T flip-flop is nothing but a complementing flip-flop. They are specially used for counters, right? I did a project along with some design students 3 years back, where I'm not aware whether you know B315 or not, right? When these biometric attendances were not there, we designed a counter circuit, very simple gate circuit only as a part of a design course, but we counted how many students are entering and how many students are leaving the class, which means that was used for taking the attendance that time when biometric system was not there. So as the student entered, there will be an ultrasonic sensor which will trigger, and then a count will be incremented. Okay, so which means that, say if your class is at 10 o'clock, after 10:05, if you look at the counter value, that shows the number of students inside the class. Okay, and similarly after the class, as students left, the counter will get decremented. So it has to be 0 at the end of the class if when all the students are left. Likewise, we designed that counter, but in order to design that counter, we used T flip-flops there. So the applications of a T flip-flop is it will count. Okay. Now, how is the inputs and outputs of a T flip-flop? It is very much similar to JK flip-flop. Only difference here is JK, if you short the inputs of J and K, that will be your toggle input. Okay. So and the internal circuitry will also remain the same. Everything is, this is actually J input, this is your K input, and rest all remains the same, right? The feedback is taken from Q bar for this, and Q flip-flop is taken from here, and all you need is you short it, this will become a T flip-flop. Now you might recall the D flip-flop and T flip-flop. D flip-flop came from RS flip-flop. Only difference here is R and S are knotted, whereas your T flip-flop comes from a JK flip-flop. The difference is J and K are shorted without any inverter in between. Okay. Now what is the truth table here? The truth table here is, it depends on your previous state, right? So if your Q of T is, Q of T and T are the inputs, because there are two inputs only. Clock we will not bother because this is a sequential synchronizing input only, so we will not bother about this triggering. So Q and T are the inputs here. Why we are not considering this? Okay, so Q and T are your inputs. So when your Q is 0, the 4 different possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. When your previous input is 0 and your toggle input is 0, there will be no change. So you will have 0 only. Toggling will not take place. When your previous input is 0 and your toggle input is 1, your Q of T will get toggled from 0 to 1. Similarly, when your previous input is 1 and your toggling input is 1, your 1 will get changed to 0. Whereas when your T input is 0, whatever is your previous input, if it is 1, your output will also be 1. So your characteristic equation from these will create Q of T plus 1. Q of T plus 1 will be T XOR Q of T. Okay. So this uses, please remember, whenever T is 1 here, it means your J and K is equal to 1 and 1. This is the property that is exploiting the toggling function. Okay, so we all know that when J and K are equal to 1, your Q of T plus 1 is equal to Q bar of T. This is what it is. So your Q of T plus 1, the characteristic equation can be written as T plus Q of T, which is nothing but the XOR of these two things. Okay, Now the characteristic table, we are doing reverse if you look, right? So first the state table and then the characteristic equation and then the characteristic table. So your T flip-flop, T, and assuming that your clock is 1 here, your next state will be represented in terms of present state Q of T. Whenever your toggle input is 0, there will be no change in your next state. Whenever your toggle input is 1, your next state will get toggled, which means Q of T will become Q bar of T. Okay, so this is what is the JK flip-flop is. Any doubt till this? Okay, next it is not a topic, just to make you think. How do you create a T flip-flop? How do you create a T flip-flop from D flip-flop? All right. So this is a logical question, but there is a methodology to do it also. Okay. So how do you do that? How do you do that is all from the Boolean expression. If you recall the characteristic equation of a D flip-flop, what is the characteristic equation of a D flip-flop? D flip-flop was just a Q of T. It is not Q, it is just a Q, right? So let me go and look at the D flip-flop's characteristic equation. Q of T plus 1 is just D, right? Yeah. Okay. So your Q of T plus 1 is just D. All we need to do is we have to create a T flip-flop. So your next state will be an XOR gate of this T. So your toggle input, when you XOR this, you will get the next state of your T flip-flop. So this simple logic is what we deploy here to implement a T flip-flop. So this is a D flip-flop, right? You XOR this with what? Your T input is XORed with your present state Q of T, which is nothing your D input here. So this will become a T flip-flop, right? And you might immediately question, how do we think? Because we have a ready-made answer here. Okay, this is fine, we understood, but how do we think? But there is a methodology behind in converting one flip-flop to the other flip-flop. We will discuss in detail. So there you can apply this technique here also. You will get the same result. Okay, so before trying to get confused, we will look at the methodology and we will revisit this particular problem again. Okay. Now we are going to look at the problems faced by these flip-flops. If you look at the way how we have placed our topics, first we introduced about the memory element and then we built on RS flip-flop. There was a problem with the RS flip-flop, we developed D flip-flop and then not flip-flop, in fact latches. And then we introduced the synchronization problem in case of an RS flip-flop. We designed JK flip-flop and then T flip-flop. Now we cannot get ourselves complacent having designed a flip-flop which is working fine for all possible inputs. Still there will be problems. So now we are going to see those kind of problems. What is that? Now we are going to analyze. It is about the synchronization and asynchronization problems. What do you mean by synchronization and asynchronization problems is because in these circuits, let me take a JK. Let me take this circuit. Yeah. If you look at this particular circuit here. Yeah, if you look at this particular circuit, you are giving a clock signal only to this NAND gates, but not to this NAND gates. So meaning you are controlling these gates, these first two NAND gates, but you are not controlling these last two NAND gates, where your last two gates are also significant. Why they are significant? The same output is fed back to the input here also, and the same output is being fed back to this particular gate also. So what will happen is this output will be, so this gate will behave improperly because it is already having an output here. And this output, if this is 0, right, this gates will be sensitive because what is the truth table for a NAND gate? When any input is 0, it will create an output. So without even looking at this S bar and R bar inputs, you will get an output which will again alter the first two gates. So this is a serious issue here. This is the problem of asynchronization. So we have to have a better control of our gates. In order to do that, so that is the problem we are going to address now. First, let us list down the problems here. What is the need for an asynchronous input? So most flip-flops here, they are provided with direct inputs, or we call it as an asynchronous inputs that will let you immediately allow to set or clear the state regardless of whatever your clock input is. All you need to do is whenever you are having an edge triggered, your flip-flop will continue to operate. So whatever till now we have done is a synchronous kind of a flip-flop. We don't have a controlled input across our flip-flops. So asynchronous inputs are definitely going to affect the independency of our clock. This is an asynchronous input only, right? When you are feeding back your output, you cannot really determine at what time you will get inputs here and what time you will get inputs here because of this feedback thing. So we have to avoid this. So what we do is, in order to bring in better control to our flip-flop. Now if you draw a block diagram of a JK flip-flop, what are the inputs we have? We have a J input, we have a K input, we have a Q input, and we have a Q bar input. And in addition to that, we have a clock input, right? This is how your Q and Q bar is. In which, if you look at the internal circuitry, we are controlling only the first two gates and not these two gates. If you want to control these two gates, then what we do is we will give two more inputs so that these two gates are controlled. And those two inputs, we are going to define it as preset and clear. What does this mean? Which means that whenever this input preset is there, right, I am going to give a preset input in addition to the already available clock J and K. Whenever I'm having a preset input here, let me have active high, my Q will be set to 1. If I want to clear my Q, then I will have clear input high. Whenever my clear input is high, my Q output will be 0. Okay, so I will have a better control now. And these two inputs, I will not feed it to my first two gates, but I will feed it to my last two gates. So let us first understand the theory behind this. So I'm going to define two more inputs for the flip-flops. One is a preset and other is a clear. Preset, in other name, we can also call it as a directly setting, direct set. Clear, it is directly resetting. Resetting means we are resetting this to 0. So whenever your preset is high, your Q will be set to high. Whenever your clear is high, your Q will be set to low. So this gives us a much better control instead of this feedback thing. This feedback thing here directly affecting these two gates. Now, if you have one more control from outside, which is a preset and other is a clear, then we will have a better control. Sorry about this highlight. Lazy to change the pen. All right. Okay. So now how does your flip-flop will work? They will operate normally till the time your preset is 0 and clear is 0. Right? If you are not giving anything here, they will normally operate like a J and K. But only if you want to reset thing, then you can use these inputs. So how do they look like this? Don't look at the internal diagram. Look at this diagram. I have normal inputs of J, K and clock. Outputs Q and Q bar. So you will have a preset input here and a clear input here. Why this is a bubbled here? Bubbled here because it represents that they are active low inputs. Active low inputs in the sense when you give 0 here, they will be active. When you give 0 here, they will be active. Okay, so that is the meaning. Why should we give active low? Why active low was because the gates that we have inside, everything is a NAND gate. We know that when you give 0 here, your output of your NAND gate will be 1. Meaning, look at the connection now. I'm giving preset here. What does preset will do? Whenever I'm having an input here, it will make my Q equal to 1. If I want to make this Q equal to 1, I have to give a 0 input here, right? Because this is an AND gate. So when I give a 0 input here, I am directly connecting my preset to my third gate. If I write it as 1, 2, 3, and 4, I directly give my third input a 0 here. And at the same time, I'm giving it to this also, so that, you know, when this is made 1, right, we are making sure that this input is not affecting this output. Okay, so that is the reason we are purposefully making this to be 0 and this to be 1. Okay, all right. Now, if my clear is 1, now look at the clear input. If my clear equal to 0, right, what will happen? Let me clear this. Okay. Now what will happen if I give a 0 input here? If I give a 0 input here, I am forcing this fourth NAND gate to be 1. If this is 1, Q bar and Q are complement of each other. So I'm forcing my Q to 0. This is how I'm clearing it. But at the same time, I'm making sure that this output is 1 so that this Q output is not affected by this input here. Right? So this is the logic behind. And the same has been explained with the timing diagram. Okay, so let me quickly explain this timing diagram. Now here we have got a problem. So that is why this timing diagram has been given here. I think I should take a break. Break in the sense we will discuss something else. Oh, 77 are here. Okay, so how many of you are aware of there was an email that I got maybe 3-4 days back.